Hi everyone, my name is Sigrid Dimta, and today I would like to present the work that I have done together with Mohammed Zahib Amjad and Professor Fatko Dressler here at the Technical University of Berlin under the topic mmWave on the road, investigating the weather impact on 60 GHz vehicle-to-everything communication channels. In the last years, a substantial amount of research has been conducted to improve the modern intelligent transportation systems, which so far utilizes the sub-6 GHz communications. Recently, the IEEE 802.11 BD standard, together with the third generation partnership project in Release 16, have supported the communication in the millimeter wave frequency band, and particularly at 60 GHz, for the vehicle-to-vehicle communication scenarios. Moving the communication to the unused millimeter wave frequency band addresses the growing demands for higher communication speed, but with the cost of a very high path loss. The increased path loss is not only an attribute of higher transmission frequency, since other factors as well further attenuate the propagating signal, such as the atmospheric attenuation and specifically the attenuation from the oxygen molecules that reaches the highest value at 60 GHz in the range of 15 dB per kilometer. Other factors additionally attenuate the propagating signal, such as the weather variations due to the comparable size of the wavelength with the size of the raindrop and the snowflake. And this also defines the main motivation of our work, which was to investigate the impact of the weather conditions through an extensive set of simulations in a realistic vehicular network at 60 GHz channels. But before analyzing the impact of these weather conditions, it is very important to understand the main characteristics of rain and snow and how these characteristics influences the propagation of the electromagnetic wave. So starting with rain. Rain, it is a liquid form of precipitation with drop diameter equal or larger than 0.5 millimeter. The raindrops reaching the surface of the earth rarely can have a diameter which is larger than 6 millimeter due to the collision between the drops and the increasing instability as the drop grows larger. The size of the drop. It is an important component that defines the drop shape, which differently from what we have seen in the literature, it is not a teardrop, but it resembles more a sphere for a diameter below 2 millimeter, and as the diameter increases, it starts becoming more flattened in the bottom and wider in the sides, leading to what has been expected an attenuation that is higher for horizontal antenna polarization compared to the vertical one. The second form of precipitation it is snow, which based on the amount of the water can be classified as dry and wet snow. Studies have shown that for frequencies above 10 GHz, the attenuation from the ice particles, such as dry snow, ice crystals, and hail, it is negligible. But this is not the case for the wet snow, the attenuation from which can be higher than the attenuation from the pure rain. Wet snow, it is formed by the snowflakes falling through air above the freezing temperature characterized by high amount of moist. Due to these conditions, the particles start melting, getting covered by a thin layer of water which acts as a glue at the moment when the particles are close to each other, forming bigger particles that attenuate as it was entirely from water but with a bigger size, leading to an attenuation which is higher than the attenuation from the pure rain. And as these particles keep melting, they will be divided into smaller drops, forming rain due to the increasing instability. A possible solution to overcome the attenuation from the weather conditions, it is to increase the antenna transmission power, but this can lead to limitations in terms of interference or spectral reusability. So another solution would be to estimate the attenuation from these weather conditions by using fading prediction methods, and the most widely used ones are the ones developed by the International Telecommunication Union, which we also used in our work to estimate the attenuation from the pure rain and combined rain and wet snow. However, recent studies have shown that the fading prediction method for estimating the attenuation from the pure rain does not perform well, particularly for very short communication distances. Slight modification of the model has been proposed to better approach the measurement results. This was not the case for the wet snow, where due to the difficulty in collecting experimental data, the only fading prediction method that has been developed it is the one from the International Telecommunication Union, which also requires some further validation. In order to study the impact of the weather conditions on the radio links, we based our work on simulations and particularly on the MilliCar model. MilliCar is an open source NS3 module that enables full stack end-to-end simulations for V2V mmWave networks. The advantage of MilliCar model over the other tools, it is related to its channel model, which has been implemented according to the 3GPP specifications for the V2V networks. The model identifies, beside the common communication conditions such as line of sight and non-line of sight, another communication condition called the non-line of sight V, which corresponds to the situations depicted in the figure, in which the direct communication between the two vehicles it is blocked by another vehicle, so dynamic blockage, which can have different heights. The height of this blockage with respect to the transmitter and the receiver antenna height, it is an important component that influences the attenuation. The main contribution of our work has been to, first of all, extend the MilliCar model by incorporating the ITU standardized fading prediction methods for estimating the attenuation from pure rain and combined rain and wet snow. And secondly, investigate the impact of these weather conditions on 60 GHz radio links in a realistic vehicular scenario. For this reason, we used the coupling implementation of NS3 with Zumo and the specific case for the Paderborn city in Germany. In our scenario, the vehicles follow each other, always assuming the presence of a line of sight communication and a horizontal antenna polarization. The intensity of precipitation that we assumed for our experiment, it was 30 mm per hour. And the metric that we analyzed has been the path loss, which has been collected for every pair of the vehicles communicating on a distance which was below 200 meters. So as previously mentioned, the metric that we took into consideration, it was the path loss. First, on the left, we show the results that has been collected by using the basic MilliCar model, or differently called the sunny day. And on the right are the path loss results that we collected at the moment when we assume the presence of combined rain and wet snow in the radio link. So in this case, we use the box plots to understand the distribution of the data over distance intervals of 20 meters. The bar shows the median, and the box plot extends to the first and the third quartile. The whiskers indicate the first and the 99th percentile of the data. The results show that for very short communication distances, like for example in the range from 20 to 40 meters, the impact of the weather conditions, it is almost negligible. But as the communication distance increases, for example, in the range from 180 to 200 meters, we can see a difference in the median values of around 5 decibel at the moment when we have the presence of the rain and wet snow in the communication link. A very interesting conclusion that can be derived from the results, it is the restriction in the communication distance due to the weather variations for a fixed value of the path loss. So assuming the value of the path loss is 110 decibel as a threshold. We can see in this case that the maximum communication distance that can be reached at the moment when we have a sunny day, it will be in the range from 180 to 200 meters. But this is not the case at the moment when we have combined rain and wet snow in the communication link, when the maximum communication distance, it is limited in the range from 120 to 140 meters. So a limitation of around 60 meters due to the presence of the weather variations. To conclude this presentation, the weather conditions such as rain and wet snow can have a high impact on the communication in millimeter wave frequencies, and even can limit the communication distance in ranges of up to 60 meters, depending on the value of the rain intensity. In order to study the impact of these weather variations in the radio links, we used the NS3 module, and we have extended it by incorporating the ITU fading prediction methods for estimating the attenuation from pure rain and combined rain and wet snow. To investigate the impact of these weather conditions on realistic vehicular scenarios, we use the coupling implementation of NS3 with Zumo and the specific case for the city of Paderborn. Our toolkit, it is open source, and we invite everyone to validate the model with more interesting simulation scenarios. Thank you for your attention.